Hello, good morning to all, or good evening, whatever suits you. Myself, Jyoti Bharti, and today I'm going to present our project report, which is based on the analysis of molecules using ORCA software and using Crystal Explorer to find the introduction energy and binding energy in the crystal. So, in this assignment, we have to use ORCA software and Crystal Explorer software to optimize the geometry of molecules, find the interaction energy of crystals, and compare their properties. So first, the questions we have is regarding the ORCA software, and in the first question, what we have to do is we have to perform the DFT calculations using B3 lift 61G DP level of theory in ORCA, and we have to perform optimization of ethylene glycol and acetone molecule and confirm their convergence and visualize their geometry and find the key bond distance, bond angle, and dihedral angle from the optimized structure and also calculate dipole moment. So what I did, firstly, I have done the optimization and frequency calculation of glycol. So firstly, let me introduce you to the word optimization. Optimization means finding the minimum energy conformation for any molecule, or we can say finding the stable conformation of molecule or equilibrium geometry in which it is the most stable one. So to find the minimum geometry, firstly we should have the initial geometry of any molecule. So initial geometry or initial configuration of atoms we can create by ourselves, and I have created it using the Avogadro software, which you can download from Google, Chrome, and any other browsers. So I will show you a little demo also using a simple molecule, like how I perform this optimization using the ORCA software and how I created the initial structure and performed the steps. So you will be clear about you can perform these in the bigger molecules also. So I have Avogadro software already downloaded in my system. So this is how the Avogadro software looks. You can use it's a 1.2 version and 1.9 version also. 1.9 version is better if you want to calculate spectra and like frequency calculations. It's there in that version, and 1.2 is good if you want to create the ESP surface and you want to do optimization and geometry calculation only, not more advanced analysis. So this is how the Avogadro software looks, and I have created the molecule. So this is how it looks. Here we have dialog box. Here we have elements. We can choose any element from the periodic table with which we want to have that element in our molecule. And there is a bond order and adjust hydrogen. Means it will adjust hydrogen to satisfy the valency of that particular atom. For example, if I have chosen here like carbon, so it will fix the hydrogen around the carbon to fulfill its valency. So by selecting this, if I will click here, see I have created the molecule of methane, CH4 I have created here. So this is the initial molecule we can use. One more thing, Avogadro can also do the optimization process. uh, Here you can see in extension there is a option to optimize the geometry, but it uses the molecular mechanics force field theory, which is a classical theory. Optimize the geometry, and here we have to use the DFT quantum mechanical theory. So we can initially we can optimize this geometry using Avogadro also, Avogadro force field theory, and now we will save this initial geometry to be used in the ORCA software. So we can save it as an ORCA input geometry by clicking the extension, going to ORCA, like generate ORCA input. So here we can generate the ORCA input, like you can see. This is how the input file looks. Here we have CH4, the coordinates of initial atoms, the method which we are using, basis that we are using. We can change it later on. So this is, or I can change it here itself, like the method which I am using. Here we have to use B3 lib DFT method, B3C, and we have to use 61G basis set for it, and we have to perform the optimization and frequency calculation together. So in this way, I have saved it, and I will like generate the ORCA input. It will generate the ORCA input, or like here already I have saved something. I can rewrite it using methane .inp file, and it will be saved here. Okay, I'm replacing it with original one, and I have closed this ORCA software for now. My file will be saved. We can see it in um, the files also. It will be there where I have saved this one. It's in my I will say that I have in my calculation folder. I have created a folder named methane, and here I have the input file. I think this file is created or the previous file, but this is how the input file is looking. This is our one. I will delete this one. I think it's the previous file. Maybe we have that calculated. So this is how our file is there, methane.inp file. Now we will use ORCA software to take this file as an input file and perform geometry optimization and give us the output and result. So what we will do, we will firstly install the ORCA software. You can install it in any browser. You will get YouTube video also how to install that. And we have to set environment also in our Windows to use it because it is a command line software. We will be using it through the command line. So now I will go to command line, command prompt, and after opening it here, I will firstly type ORCA. Like see, if this is showing like this, that you did an input file example IP means you have set up the ORCA in your system. So I will go to my folder where I was doing the calculations. Here in calculation, I have created the methane folder and I can see the methane input file is there. You can see. Now what we have to do to submit the job for optimization, the command line we will use is type ORCA, we will give the input file and we will tell it to write the optimized process to the methane.out file. After entering, it will take some time because we have created, we have like done the optimization also and the frequency also. We have mentioned that in our input file. So it will take some time, or we can also check in our folders. That's what's going on in these folders. I have methane one. See, there are so many files created, and its sizes is being changed on because the job is right now running. I think here the job is running, and after it's completed, it will again give us the default thing. Okay, it's completed. We can see. So I think we have created so many files. These are our final. So now see this much files we have. Now to confirm the optimization, what we will do, we will open this Gaussian output file in a notepad manner, and we can see that this is our output file for methane. And if we will drag it down in the last uh, to confirm, we can see that here they have mentioned ORCA terminated normally. So normal terminated means whatever job we have submitted, it has done the job properly. There is no error. Otherwise, there is some error. It has taken the time 31 seconds and some milliseconds for this. And see if you will go above, you will see the gift free energy also, total enthalpy also. These are the information you can get. Electronic energy, vibration energy. So this is the main file from which you can get every information. You can search for particular keywords also, energy confirmation or the STF fashion they have done, electric properties calculation, optimization run done. These they have done the optimization completely, and then after that they did the STF property calculation. And in this way, you can analyze this file. You can have a look in this file, and you can find the important properties from this file. So this is how the file looks. You can also visualize this file using the software. So in our project, similarly, like the way I did for methane to show you all, I did this for glycol also and also for my molecule acetone in a similar way. And this is the optimized geometry which I got, this one. So this is the optimized geometry I got it. Uh, and the convergence criteria I will show here. It has shown that optimization has converged from the output file. I have confirmed that this is the optimization process has been confirmed. And then I have calculated the bond length, bond angle, and dihedral angle in this molecule. So I will also show you how can we do this from the Avogadro software. It's very simple. It's not very difficult. You have that opt.out file. What you have to do is this opt.out file you already have. You will open the Avogadro software, and in Avogadro software you can visualize the output files too. So what we will do, we have this opt.out file in our system. Uh, let's see, taking time to just go here. I will check it once. Uh, so this is the opt.out file. I will just drag it in the Avogadro software and see, open it. So this is our optimized domain. Okay, this is the optimized geometry. You can rotate it. And now to find the bond length, bond angle, we have to just select this one here. You will also get a dialog box appearing that what this tool is doing. So you have to select two atoms. You can get the bond distance of any atom manually. You can also do. Here we have so many other spectra you can also calculate, but I think it will be in the 1.9 version. It will show the spectra because 1.2 version doesn't show this. Spectra we can calculate so many things that we can create surfaces also. I'm showing you all these things in here. We will be doing it in the further thing. Electrostatic potential surface calculate. Okay, it is not yet supported, so we will have to download this the 1.9 version. So in this thing you can it will in the 1.9 version it will show all these things extension you can get many things like spectra, create surface, crystallographic axis, and more advanced analysis you can do in the 1.9 version. And here I have shown you like you can select two atoms, can find the bond distance here in the left corner down. Uh, by selecting three atoms, you will find the uh, bond angle. Selecting four atoms, you will find the dihedral too. So you can do it manually also, or also like in the 1.9 version, it will give you the atom properties and will show you the dialog box there. So in this way, you can analyze using software Avogadro, the post-processing you can do after optimizing to ORCA. So what I did similar. I just optimized the glycol molecule and then I calculated the bond length, the important bond length, bond angle, and dihedral angle, and also the energy of this molecule I got from the output file I have shown you. So this is the energy we're getting for this ethylene glycol molecule. Similar process I did for the acetone molecule too, and we have created the initial geometry, and then what we did, we created the initial geometry and then we optimized it, confirmed the optimization in the similar way, and then uh, the energy values I got the output files from the output file I showed you, and the bond length, dihedral bond angle I have got from the Avogadro software. And also we have there was a question that we have to mention the dipole moments also. So the dipole moments question also you can either you can use the Avogadro software and you can get it from the output file. So the output file which I showed you is a very important one. You will get every information. This bond data also you can get from the output file by searching the keyword. So dipole moment also I got from the output files for of both these molecules and have mentioned here. So this was the first question which we did using ORCA and Avogadro. So the second question was using the ORCA software to find the glycine spectra, IR spectra. So in the similar manner, firstly I did the optimization and the frequency calculation of glycine, and then what I did, I used the optimized geometry and the way I showed you create a spectra. And in the 1.9 version, we can keep spectra because 1.2 doesn't support that. So you have to download the both. Like 1.2 for creating the input files because it will be more favorable in that one, and 1.9 version to create the spectra. Like see, we have there you can get the optimal analysis and plot spectra, vibrational modes also, create surface also, and there you will get the electrostatic surface. So we got the IS spectra for glycine like this, and we got a paper also. I have mentioned the reference. So this is the paper. So the paper we can see like the peaks which we are getting is quite bit matching here. Like the peak we are getting near 3,360 here one, and like we know that in eye spectra the range till 500, from 500 to 1500 is a fingerprint region. After that it's a like characteristic thing. So here the peaks we are getting small peaks and around 3,000 and all, and here also we have after 1600 we are getting a broad peak around this one. So it's like quite matching with our theoretical one and experimental one also. Also there are some deviation because in experimentals we have solvent effect also and other things also, but in DFT calculation we are considering only a particular molecule of glycine. So this is the data we got, the wave IR spectra data. And after that, what the question was, the third one was to find the trans and cis geometry of 1,2-dichloroethylene. So in a similar manner, we firstly created the input geometry, then optimized it, and then got the output files. And from the output files, we get the energy values. And we can see that the energy values that both the system has almost similar energy in the heart rate they have mentioned, but we can see that this system is little bit more, stable than the trans. So the reason here is we found that it's because of the cis effect. Because in cis effect, what happens, then the chlorine will donate a lone pair and will donate a lone pair to the double bond, and it will get delocalized. So it will get a positive charge, this chlorine. I will show you from the this one. So this fluorine will get a positive charge as it is like donating its lone pair. And by delocalizing through this double bond, this chlorine will get negative charge. And now we will have a electrostatic attraction between these two. But in the case of trans, the positive and negative fluorine will be far away as compared to the cis one. So this is called cis effect, and that's why the cis one is more stable because of the electrostatic attraction between these two chlorine molecules. So now the data is also confirming that cis effect here. Now the next question was to plot the HOMO and LUMO of butadiene. So to plot this, what we did, we have to use another software which is called iView. So firstly, we created the initial geometry, then optimized the geometries in ORCA software, and after getting the file output file, what we did, we created we downloaded the IO view, and then we created using a command a molten command which we use in orca underscore like mlk, and the input file which we are using and the molten thing, we will create an input file for the IO view one, and by dragging that input file to the IO view, it will create the orbitals and homolumo for this. It's downloading overview. It's very simple, and also it is similar like Avogadro only. You have to only drag the file there, and the command you have to use to create this input file for overview. And we got this homo and lumo, and we can also confirm it from, and as we all know from the literature. So in the homo we have only one node, and in the lumo we have two nodes, and energies like in heart rate, HOMO's energy minus 0.22 heart rate, and energy of LUMO is minus 0.0236 heart rate. So this is how we calculated the HOMO and LUMO of butadiene. And the last calculation was the calculating electrostatic potential map for ethanol and DMSO. So ethanol molecule, like we firstly optimized it, and then we used the create surface option, which was there in I showed you in the Avogadro. So we use Avogadro to create a surface, and here the blue region is showing the positive region, and the red region is showing the negative region. So we can see from the graph also here in the oxygen, there's a red region because oxygen is more electronegative, and in this case we have the sulfur a little bit more electronegative, showing by the red one, but not if the color is little bit faded away because it's not more like electronegative like oxygen. Also, we have to calculate the partial charges. We can get, like I told you, from the output file also, from the Avogadro properties. Avogadro, you will get an atom option, and you can show the properties of atom, and it will show you the partial charges present on that atom. So, like mainly what we are doing is we are performing the geometry optimization in ORCA, and then we are post processing or analyzing the data using the Avogadro software, and it's very easy. It's a user interface, graphical user interface, user friendly software. So we have to just click on the particular dialog box. We can explore more things like we want to calculate IR spectra, we want to calculate the ESP thing, van der Waals surface also we can create, and we can know the partial charges, energies each step also, like while optimizing that through the steps. So at each steps, what were the energies you can calculate. So this was the part for our ORCA software. I hope you have understood how to use the ORCA software. I showed you also one calculation, and downloading ORCA is very simple. You can see it from the like YouTube videos, how to download, how to set up environment, and then the simple command you have to use, which I showed you also in Avogadro. You can do all this. So it's very simple. It's not very difficult. Avogadro, you should also have the 1.9 version as I told you because it's more favorable there. Because I just showed that I showed you in 1.2 version, it was not supporting some ASP things, and Spectra also it will not show you. So 1.9 version is good. You can get all these things from there. So this is the part for Orca one. Now we will be proceeding for the Crystal Explorer one. So Crystal Explorer, what we do is Crystal Explorer is a software to use it for for finding the interaction energy between the crystals, like how they're interacting. So we were given the two polymorphs, like they have similar structure, different arrangements. So 5-fluorouracil 1 and 5-fluorouracil 2 we were given, and we have to find the lattice energy for these two molecules or crystals. So what we did, I will show you it a little bit from this thing also how I perform these calculations, and I can show you from the Crystal Explorer site. So this is a Crystal Explorer site. You can visit it like in your uh, browser, or you can download it too. What you have to do is here they have given the manual also how to use this energies, how we are using. So if I will show you the Crystal Explorer one. So Crystal Explorer one is it calculates total energy of the system using this formula. Like you can use different methods, 61G, BT, LIP 61 GTP, Hartree power method, DFT method, interaction energy. So here what we have used is we have used the CeB3 lip method to calculate the interaction energy between a pair of molecules, and they have also shown us how we can calculate the interaction energy between a pair of molecules. So I think if I will show you a little bit how I created this, if it will be working. Uh, this is how the Pixel Explorer will look like. So you can download, like what you have to do is you have to just open the file, whichever file you have. You can download either download from the software or any zip file if you have. You can have this one here. Like I don't think it's there a zip file I had in my calculation. We can search like this one. Like for example, I have this zip file. You can open any zip file here. It will get open here. So this is a structure I have. You can see how it's there. Just open this file. You can, what you can do is you can search the neighbors, like for example, like you are finding the interaction energy. So means you need to have the other molecule also, other neighborhood also, or lattice energy to find. So you have to create, like I'm using 3.8 angstrom for example, or 2.5 angstrom. You can also use. You have to find it out, like which things you are calculating and to which distance, to which radius distance you are calculating that energy. So these are the atoms which are in the 2.5 angstrom. I will complete the fragments using this. So these are all the fragments which are in that region. So by selecting this one molecule, we will we can just calculate right here the E to calculate energy. We can use the accurate one, basically, and fast one. This fast one is hard to talk. For now, I will be doing fast one. Just okay, and it will show the wave function calculation in progress here. And the guy is running. It's showing that the calculation is being processed. It's a like in a brief manner. I'm showing you how did I calculate it. So what I did for my thing, I have to calculate the lattice energy as I showed you. So I have like here it's just interaction energy how we can calculate. For lattice energy, they have the manual. You can see this that using the CBC model energies, uh, they are using it for calculating lattice energy. So here, if you will read it a little bit, you can see, and I can show you the particular paragraph that the lattice energy is obtained as one half of the product of the two columns labeled as N and E total. So after the calculation will be finished here, you will get a pop-up menu like this. Here they have given the N, like and it's like a similar atom, like center we are considering our one crystal, and from that center, like at the particular radius, how many similar atoms are there, and the symmetry operations, then the contributions, as we can, I can show you if it's there, like the electronic contribution to the energy, polarization, dispersion, repulsion thing, and the total energy there. So how we can calculate the lattice energy is by uh, lattice energy is like multiplying this n column with the a total column for everything and then dividing it by 2. Dividing it by 2 is because we are calculating that is energy in kilocalorie per mole. Here I have mentioned the values like kilojoule per mole. So to avoid the, like if A is interacting with B and P is also interacting with it, to avoid the double counting of these things, we are just dividing it by 2. So I did, and I have taken this radius as 15 angstrom radius, not 3.8 angstrom here, because if you will, like here is going on, if you will see in the site what they have given, see, they have mentioned here for calculating the lattice energy if you have one molecule unit cell. So if you will see for non-dipolar molecules, radius of 20 angstrom should be adequate, and for more dipolar molecules, radius of 30 angstrom should be accurate. So this we have done based on the convergence criteria. You know, like after how many radius uh, I will take so that the energy is not changing much. Okay, we have they have used the convergence criteria. We can also use it. Will take a more time, but we can use the convergence criteria to see that how much angstrom should I choose to get the latest energy. So in this, so by default also I use this one which they have mentioned here, close to 15 angstrom, and then I calculated the thing here, this latest energy thing calculated, and I got for one polymorph is minus 121.75 kilojoule per mole, and for other it's minus 135.2 kilojoule per mole. So this is the first thing I did. Similarly, I calculated pi static energy for pyrene. I did similar for pyrene case. Firstly, we uploaded a zip file there, and then we calculated the radius distance and completed the fragment, and then calculated the energy. So here the total energy is written, I showed you like this, the scaling factor and the particular contribution of electronic thing, polarization energy, dispersion, and repulsion. As we know, in the pi stacking, it's mainly because of dispersion, because of the quantum fluctuations of the electrons, they get moved and create a, you know, polarity for instant time of for small period of time, and then that's why they are just there is a attraction between these two layers. So this is because of dispersion. So pi taking energy, I have mentioned here, this pi energy is minus 145.283 kilojoules per mole, and also we have calculated the lattice energy using the same formula, which is minus 106.8 kilojoules per mole, and repulsive energy is like. So why I have mentioned the repulsive energy, because as we can see, the lattice energy is less negative as compared to pi energy. So if I will calculate the contribution, it will come more than 100%, because obviously we are seeing that it's more negative. But why it's more negative? Because while calculating the lattice energy, total lattice energy, we are taking into consideration the repulsion part also, which is the positive energy. But in dispersion calculation, the pi thing, it's only an attraction thing. So it has only the negative portion. So these are the values I have mentioned, which I got from this calculation. After that, what we did, the hydrogen bonding we were getting in the case of uracil, like particular electrostatic energy, because hydrogen bonding is electrostatic one, and the pi stacking energy which we are getting in the case of pyrene. We compared these two both, and we found that the pi stacking energy is more negative in the case of pyrene as compared to the hydrogen bonding in case of uracil. So that's why we concluded from here that although dispersion, like sometimes it's uh, weak also, but here we can see that it can add up to a significant amount for stabilization. In case of pyrene, the most stabilizing factor is dispersion energy, as we also saw that it's very negative compared to lattice energy also. So the in case of pyrene, dispersion energy is contributing more for stabilization as compared to the hydrogen bonding in case of pure. So this was a project. We have used ORCA software for the molecules, for their bond distance, bond order, IR spectra, their ESP surface, homolumo thing, and we used this crystal explorer for finding the interaction energy, binding energy, lattice energy. So here I conclude this thing, and if you have any doubts, you can text me, mail me anytime. I will be happy to answer your questions. So this is it from my side. We can see that if it has ended or not, it's still running. Energy calculation is in progress. Once it will finish, so it will pop up. There will be a pop-up menu we can show, and it will there will we get total energy, electrostatic part, and dispersed energy part, repulsive part, and we will get the n values, total values, and using the formula which I told you, we can calculate that is energy, and we can also find the particular like contribution of particular dispersion energy, electrostatic energy, repulsion energy to that total energy. So I think still running, but because we have used fast also, it should do fast. But this is the same way we will get. We will after it's completed, we will get a pop-up menu which has been shown in this side to this thing, and we will just use the formula. See, this pop-up menu has popped out because I think it was finished. Yeah. So this is the thing we got. Like center molecule we have chosen. This red one are the similar, purple one are similar, and values we got. We have the electrostatic term, polarization, dispersion, repulsion, total. So we can see like these are the scaling factor they have used to calculate the total energy. So we can see that total is minus 22, like in case of these two red molecules, and repulsion is very high also, 107.8, and mostly it is electronic things uh, giving to the total energy. So in this way, you can analyze data, and you can also use different molecules. I have used a random zip file here, and we are getting this particular contribution in this file. So this is uh, it from my side, and I hope you have learned something new from this. You have learned the optimization thing, interaction energy thing, and thank you so much from my side.